Hello everybody. This is our experimental design analysis speech. We chose to look into the shape of rocket heat shields, specifically which ones are most effective when not in the environment of space. My name is Eric Bliss.
My name is Zach Bruckner.
My name is Aanika.
And I'm Aanika Cole. So the first thing that we're going to look into is an introduction. We're going to hit 4 different types of heat shields, which are square, hexagon, circles, and lastly triangles.
The next part of our project is to experiment, and we are going to look at which heat shield shape works the best.
And finally, we'll look at the results and we'll look at which heat shield worked the best and why it worked the best.
So for our introduction, we are going to look at the different types of heat shields. To start off, our prompt coming into this experiment was to try to understand why NASA chooses the heat shield shapes that they do. We know that they are currently using some specific shapes, but we were wondering if whether this is because it works the best or because it works the best with the materials that they have and their conditions. Maybe there is a better solution to this, but on a smaller scale, which is where our project comes in.
Now picture this. You're in space and you need a heat shield. Think of what materials and what shape you think would be best to use the most heat resistance.
Alright, so we're going to look at our types of heat shields that we chose. We thought that our control shape is going to be a hexagon because we know that that is a shape that is currently being used by NASA, and it is what we hypothesize is going to be the best shape.
Next, we'll look at circle, and it's a newer shape with 0 corners and it's just round.
And then we're going to look into squares, which is also a new shape, which has 4 sides and 4 corners.
And the final new shape that we used to test was the triangle, which has 3 corners and 3 sides.
So first we're going to look at the hexagon heat shield shape. And we decided this to be our control because it is currently being used by NASA on one of their newer space telescopes, the James Webb Space Telescope. After doing research, we found on the NASA website that they use the hexagon heat shield shape for 2 main reasons, for the shaping and the design. First off, the shaping of being a hexagon allows the shield to cover the most amount of surface area to protect the rocket or spacecraft without having very many breaks in between, allowing it to be the most effective. We also learned that on the James Webb Space Telescope website, the design was specially created into a parasol shape, which, like you see in this picture, is slightly bent outwards, meaning that the sun bounces off the shield and goes back in the direction it came from, keeping the heat away from the telescope and allowing it to fold up before and after use, which is very useful.
Now that you've seen a successful example of one of NASA's sun shields, can you think of what kind of factors they maybe had to take into account while creating it?
Okay, so the next heat shield we're going to look at is a circle heat shield. And NASA's example of this is the hypersonic inflatable heat shield. And what it's used for is to help spacecraft enter and leave the atmosphere while keeping it at a stable temperature. Its shaping, like I said, is round, and it absorbs and kind of pushes heat away from the aircraft, which is what ablative is. And the design of it kind of depends on the mission requirements, and they kind of test these heat shields through computer simulations and wind tunnel tests.
Now we're going to look into square heat shields. According to encyclopedia.com, square heat shields tend to be made from both silica and ceramics. There are 2 different types of tiles that they use. These are known as high temperature reusable surface insulation, also known as HRSI tiles, and then low temperature reusable surface insulation tiles, which are LRSI tiles. Both of these tiles, so HRSI tiles tend to be made from 99.8% silica, and they range between 2.5 to 12.5 centimeters and are 1 to 5 inches thick. Then when looking into LRSI tiles, we see that they are 20 centimeters by 20 centimeters. When making square heat shields, they tend to put HRSI tiles on the top as they tend to have more heat resistance, and then LRSI tiles on the bottom as they tend to have a lower heat resistance.
No, unfortunately for my shape, the triangle, there weren't any examples that I could find of it actually being used in a real heat shield. Its design is pretty weird since it has 3 corners, obviously, that are each much farther away than each of the midpoints of the 3 edges would be, so it creates for an odd flow of heat around the shape. Because it's never been used, the materials it would be built out of haven't really been explored, but it would presumably be similar to Aanika's maybe ceramics and silica if it were used in tiling, or something like beryllium if it were used in a sun shield.
Okay, so now for the experiment, we're going to look at which heat shield shape worked the best. But before we start that, we want you guys to make a choice. Which heat shield shape do you think worked the best?
All right, so first we decided to look at our unsuccessful designs. And unfortunately, as with many experiments, this is what happens. So first, we had an original design that had the hairdryer on the side, a heat shield in the middle wrapped in tinfoil with tiny little cutout shapes of our original shape, like this. It originally had that wrapped in tinfoil and then to the side of the ice cube on our plate. Unfortunately, this did not end up working because the heat would bounce off the heat shield and go in many separate different directions. And thanks to the conditions of that environment as well, this just did not get to the ice cube and did not prove what we wanted it to be testing. So we decided that this was an unsuccessful design and that we need to think of a new design.
Then we had to redesign a little bit, and it took some thinking, and then we made our successful design. When looking at our successful design, we had to change where we placed the hairdryer. So we moved it from being to the side to the top. Then we remade our heat shield. So instead of having many small shapes put together, we made a smaller scale one, which is only one shape like this. And we placed it right underneath the heat shield, about 5 centimeters under. And then we had the plate underneath with the ice. This allowed the heat to be still resisted, but allow it to go around it, giving us the results that we needed.
Now, as for actually conducting the experiment, this is the kind of step-by-step process that we followed. First, we actually made the cardboard shapes. Then we set it up in this, or an approximation of this scenario where we have a plate with an ice cube, then heat shield 7.5 centimeters above that, and a hairdryer 5 centimeters on that. Above that, then we turned on the hairdryer, pointed at the shield with the ice cube beneath it. We timed it until the ice melted, and then we recorded both that data, how long the ice took to melt, as well as how much ice had actually melted, and then we repeated all the previous steps for each of our 4 shapes.
Okay, so now we'll look at some of the materials used. So first off, we used the hairdryer to kind of melt the ice, as well as we used prongs to hold up these cardboard shapes. And then we also used a crusher thing to crush the ice cubes into smaller pieces. And we also used a plate to hold the ice cubes. So now we're going to look at the results and which shape worked the best.
But first, before we do that, our original hypothesis, which isn't as relevant to our end experiment, but we still stuck with it, was that the hexagon was going to be the best heat shield because NASA has used it, so it's obviously tried and tested. But it also has radiant or 6-fold symmetry, which it can fold a lot of different ways, and that also means that it has roughly equivalent distance from the corners to the edges and the edges to the center. So we thought it would give a good distribution of heat flow around the shape.
All right, so when we looked at our results from our hexagon tests, we found that the time the ice cube takes to melt is averaging about 1 minute and 22 seconds. Now we don't really know how this compares to the others yet, so we don't really know how well this is, or how good this is, but we recorded the amount that melted off, and we found that this did vary slightly from time to time, which would make sense because in a real-life scenario, this does have some variation. And we found that the melt-off time ratio is about 8.8367 milliliters per minute.
And next for the circle, this one worked a bit better. Then the hexagon, as it was 2 minutes and 18 seconds at an average, and the melt off to time ratio was about 5.7 milliliters per minute.
Then when looking into the square, we noticed that this one had a pretty good average compared to the previous two. We saw that it had an average time of 2 minutes and 24 seconds and about 5.46 milliliters per minute.
Now, my shape, the triangle, had an average time of 1 minute and 22 seconds and an average melt-off to time ratio of 7.7. We've been using that statistic for each of them and haven't really explained what it means. It's just how much water melted off the ice per minute. Higher numbers mean the shield was less effective, and so the triangle kind of sucks.
So now we'll look at the best heat shield shape, and we found that the square was the best as it had an average time of 2 minutes and 24 seconds till it fully melted. And we found that it covered a lot of area with a small amount of material. And if multiple of these are used, it can attach without space being lost in between, and which means it can be much more effective than some of the other shapes we tried.
This means that our hypothesis was incorrect. Our best guess as to why this is because a hexagon is just too many corners and too many sides, because it and the triangle both did very badly, while the circle and the square were the best. So our guess is that you either need to be pretty much perfectly circular to evenly distribute the heat, or have a medium amount of corner to side where it has the weird distribution.
So to conclude, we found out through our experiment that there are many possible shapes that can be used as heat shields, such as the hexagon, square, circle, and triangle, but we did find that the square works the best. We also found that the experiment may need adjustment before we can conclude that it works correctly, which is how we found with our successful and unsuccessful experiments.
So now, we want you guys to look at your original heat shield design, and we want you to see, now that you've looked at all of ours, what kind of changes you can make to yours to make it work better.
Thank you for your time.
Thank you.
Thank you.